Hello, my name is Adewale Ogabi. The title of this work is Data Fusion of IoT Appliance Traces and Satellite Solar Irradiance for Energy Efficient and Robust PV Battery Sizing under Uncertainty. This work presents a quantile-based data fusion pipeline that merges IoT appliance traces with satellite irradiance. Current design method in industrial or residential PV battery sizing, they are often based on averages or simulated loads. And this approach do fail to capture day-to-day variability, and it results in PV battery system that is being oversized, or do not meet the demands of consumers. And this is where this study comes in to use evidence-based scenarios which combines real IoT appliance load with satellite solar information. So to do this, we fused two data sets which are from IoT appliance data Echo CO2 smart plugs. This consists of 42 devices from 13 UK homes. So this gives us a daily household energy use in kilowatt hour per day. And also we take data from NESA Power. Middlesbrough in UK is taking as a case study, taking the solar data for January to March 2025. The DNI, DHI, and Clearness Index were extrapolated to calculate the global horizontal irradiance. So these are the data sources that has been provided for reproducibility in this study. Three level framework were identified in the study: the data level, the feature level, and the decision level. At the data level, the IoT is the sample to generate continuous household load profile, and the feature encompasses daily household metrics that are merged by date with NESA power solar metrics. The decision level is where the fused data set is stratified by quantiles to create representative data and demand supply scenarios. So I have beside here the schematic of the framework which was employed in the study. Here, the equation and the assumption used in the system models were given. The global horizontal irradiance is measured in kilowatt hour per meter squared per day. The energy demand is given in kilowatt hour per day, and the PV array area is given in meter squared. The installed PV capacity is also provided in kilowatts. Usable battery capacity is also provided in kilowatt hour. We have the DOD, which is the depth of discharge, the battery round trip efficiency, and the inverter efficiency. The baseline assumption that were made in the system model includes the module efficiency that is taken to be zero point 0.2. The system performance ratio is taken to be 0.75. The PV power density is taken to be 0.2 kilowatts per meter squared, and the depth of discharge is taken to be zero point 0.8, and the battery round trip efficiency taken to be 0.92, and also the inverter efficiency taken to be 0.95. So this plot gives us the result of the fused IoT and satellite daily profile. The load versus the solar irradiance profile shows a stochastic pattern, which is a weak dependence. The average daily solar irradiance is 1.588 with minimum of 0.152 and maximum of 4.645. Daily house load from the data that were collected ranges between 0.9 to 3.2 kilowatt hour per day. So from there, full spectrum operating scenarios were built using statistical quantiles from the fused data set. We have the demand quantiles that ranges between P10, P50 and P90. The P10 represents a day of low energy use, the P50 represents a day of typical energy use, and the P90 represents a day of high energy use. And on the solar quantiles, we have P50, which shows a typical winter solar day, that is a typical GHI, and P95, which shows a high winter solar day. So the scenarios were combined between P10 and P50. What we are trying to do here is that we are combining a scenario of, let's say, a P10, which is a day of low energy use, combining it with a typical winter day, whereby we have a typical GHI. So combining these to give us a low stress case. And the medium shows that a day that we have typical energy use and a day that we have a typical solar availability will give us a median operation. So applying the sizing model to the quantile scenarios demonstrate how significantly system requirements can change. Scenario-based sizing revealed a 5 variations in PV capacity. And from the data sets that were explored, we have the scenarios that we use to give us the load and the solar capacity. For example, fusing a P10 and P50 gives us a load of 1 and a solar of 1.12. What this means is that a scenario of P90 and P95 that is taking a high load and a high solar availability will be able to cater for a 3 kilowatt hour per day of load when 3.98 kilowatt hour per meter squared per day solar capacity is used. Also, from the solar irradiance and the load profile, we can see a quantile scenario trade-off whereby each point on this space represents a specific data-driven scenario that evaluates the trade-off between cost, resilience, and performance. For example, fusing at P90 and P50 will give us a high cost and high resilience, and fusing at P50 and P95 will give us low cost and baseline performance. Also, for validation, three methods were used for comparison: fixed quantile, mean deterministic, and random pairing. Here, after normalization, the Wasserstein distance are equal for the load versus GHI, given to be 0.163. Here, the framework preserves real-world statistical fidelity. And on the other hand, the monotonic relationship between load and GHI is captured by Spearman correlation, where the fused is given to be minus 0.2 rand and random is given to be 0.04. So conclusively, moving from assumption-based to evidence-based system design, we built a quantile-based IoT satellite fusion pipeline where PV capacity is seen to be the dominant factor in winter at low solar level. Storage on batteries beyond 2 days shows a diminishing returns. The framework allows designer to quantify risk and choose configuration that balances affordability and resilience. Yeah, many thanks to NESA Power and EcoCO2 for their contribution to open data sources, and all the scripts and data retrieval that are used on this project are available publicly on GitHub. Thank you very much.